So here's the global mean temperatures. The individual dots on here are the annual values estimated, and then there is a blue curve on here which is sort of like a decadal value. It's more of a smooth value going through these black dots, and then there's an error associated with that which is given by the yellow on here. And so there's some wiggles in here, and some of these are, if you like, natural variability. And then in more recent times is this trend, and it's mainly since about 1970, about in here. This is the part that we think is really associated with the increases in greenhouse gases in the atmosphere, and I'll show you evidence for that later on. There are different ways scientists tend to characterize this kind of a curve. One is to put a straight line through it, and if you do it for the last 150 years, it looks like this, and this is the rate of increase down the bottom here. If you do it for the last 100 years, it looks like this. If you do it for the last 50 years, it looks like that. And if you do it for the last 25 years, it looks like that. And so you can see the rate of increase is systematically increasing. So now temperatures the last 25 years are going up about 1/3 of a degree Fahrenheit per decade. These are all units per decade. And so in other words, in 30 years, you get about a 1 degree increase in temperature. And that's about what we've had in the last 30 years or so. Another way of looking at this is, what are the warmest years on record? Well, it turns out 11 out of the last 12 years are the warmest on record. The one that's missing on here is 1996, and that's replaced with 1990. We can also look at it in land versus ocean. So here's the land temperatures and the sea surface temperatures on here, and there's a difference between these. This is the difference up here. And since about 1970 in particular, the land is taking off and warming faster than the ocean. And so that's one of the things that we also expect in association with increased heat being available. The land can respond much more quickly, and it is. A key part, though, when we're talking about global warming, is that we're not just talking about temperature. As I showed you with the global heat flows through the climate system, the main way we cool the surface of the Earth is not through radiation or through the direct transfer of heat, but rather through evaporation and evapotranspiration. And so if global heating is occurring, some of that heat, a lot of that heat, in fact, goes into evaporation. And over the oceans, there's plenty of water, so it goes into evaporation rather than into raising temperatures. Some of it goes into raising temperatures. How does the human body have such a constant temperature? When you go to the doctor and you have a fever, he takes your temperature and uses that as an indicator to see whether there's something wrong and you've got some kind of a disease. And it's quite remarkable that the human body can keep such a constant temperature. And the main way it does it is indeed through perspiration and evaporation of that perspiration from your surface of your skin. In the summertime, when you've got really humid conditions and your body is trying to put out more perspiration, more sweat, but there's too much humidity in the air and that sweat can't evaporate, that's when you get very uncomfortable. And there were some occasions that happened like that this past, when was it, August in particular, record high dew point temperatures. So that's a very important process. Out in the West, where the humidity is less, we can use evaporative coolers instead of air conditioners, and so you moisten the atmosphere at the expense of, you can keep it cooler, but it ends up with a moister atmosphere. And so this works for planet Earth as well, over the oceans in particular, and it works if there's water available. But if you run out of water, if you have a drought, if you have a desert, all of the heat goes into raising temperatures and drying things out. So that's when you get an increased risk of wildfire, and you get an increased risk of heat waves as a consequence. Another example, if there's been a shower, if the ground is wet, the first thing that happens when the sun comes out is that the puddles dry up. And then the temperature starts to go up. It's not quite that simple. Of course, both are really happening together. but it again illustrates the importance of where does this heat go and the importance of water. Now, water vapor does play a role in all of this, but it comes about through the subsequent changes in temperature that occur. There's a very fundamental law. It's actually called the Clausius-Clapeyron equation, which says that the water holding capacity of the atmosphere increases by about 7% per 1 degree Celsius increase in temperature, or about 4% for 1 degree Fahrenheit increase in temperature. This is very fundamental. It's the whole reason our weather works. If you have air at the ground and it rises and expands and cools, it can no longer hold the water vapor because it's cooler, and so it drops it down, and so we get rain. It's the whole way in which rain happens and snow. You may have heard the expression, freeze drying things. Well, freeze cooling things down and drying things. If you've seen an air conditioner work, it wrings the moisture out of the atmosphere as you pump it through and you get rid of some of the moisture as a process related to that. Well, there's consequences of this. It turns out the temperatures have increased over the oceans by 1 degree Fahrenheit since about 1970. And going along with that, there has been an increase in water vapor in the atmosphere by 4%. We can measure that. We can measure both of those things. And so over the oceans, there's a 4% increase in water vapor now compared with what was about 1970. Over land, there's also been an increase in water vapor. It generally averages about 2 to 3%, but there are some places over land, like deserts and in the southwestern parts of the United States, where there's not enough water vapor, and so it's water limited, and so there the temperature just goes up. And so the availability of water affects just how responsive this is. But it means that in general there's more water vapor in the atmosphere. If there's more water vapor in the atmosphere and you have a weather system, any weather system, whether it's a thunderstorm or a big extratropical cyclone that has a cold front and a warm front that you see on satellite pictures that the television meteorologists put on the air every night, these things just reach out and grab the available moisture and suck it in and then dump it down in the form of precipitation. Most of the time it doesn't rain. How often does it rain? 10% of the time? Actually, the estimate globally is that it's raining over the globe around 7% of the time, 1/16. So on average, when it rains 16 times harder than it does evaporate. And therefore, any weather system, in order to rain, has to reach out over an area 16 times the area where it's raining in order to gather the moisture, in order to get the rain to fall at the rates that it actually does occur at, because it can't be compensated for by evaporation. Evaporation is too slow, but evaporation is occurring everywhere and it's occurring all the time. Rain is intermittent. And so, if there's more water vapor in the atmosphere, it gathers more water vapor in and it rains harder.